to talk about generative base classifier today. Okay. So again, our framework, we are doing classification, and there will be a little bit learning theorems if I can cover, maybe next time. It's about discriminative classification versus generative classification. What's the theoretical reasons or situations? One is better than the other. All right, so we categorize the classification algorithms into three kinds. The first kinds we covered is instance-based classifiers. In fact, there's no model here, right? So it's just there's no model, there are no parameter. The only thing is hyperparameter, number of neighbors to pick. So you're using the training observations as part of the model. And then the second category, the bigger category we covered, is discriminative classification. The logistic regression, support vector machine, and deep neural nets, they all follow this category, and just they're all modeling the y conditional x, and more specifically, if it's a probabilistic formulation, it's the logistic regression and neural nets. You're using a probabilistic prediction to model the y given x, but SVM using more. There's no probabilistic formulation in that classification decision. And then in the generative model, which is what we're going to cover today, is using a probabilistic formulation to perform classification. And this is the roadmap. Again, we're in the base classifier, where when you're using the probabilistic models to try to perform classification, and then through the MAP rules, those type of classifier are called all under the umbrella of base classifier. Okay, so just a little bit of review, because we already covered, right? So the base classifier uses MAP rules, maximal A posterior rules, to perform classification. So the most important is you have to be able to estimate PC conditional X. So here C is our output variable, X is our input variable vector. So because we normally have multiple input features, that makes a random variable vector. So the whole fundamental is I'm using PC conditional X, and whoever give me argmax, here the arg is that specific classification values, give me the largest. I'm predicting my classification label as the one give me the largest conditional probability. So this is the MAP rule. In the testing phase, you're really just trying to find the one, give you the largest, C star, and then and then in the training phase, actually this is what you use in the testing phase, and this, in the end, this is how you're using to perform testing or perform inference. And the learning, while you're learning this type of model, the fundamental is how do you estimate this from data? So what do you even mean estimate this from data? And the variations of the base classifiers, it's about what is this probability distribution, what probabilistic model you're using to represent this. And so there are two bigger kinds. I mean, we can separate base classifiers using into discriminative base classifier or generative base classifier. The differences is the discriminative classifiers directly modeling PC conditional on X. So your input is X1 to XP, your model gives you directly that probability, this conditional probability C over X. And then the multi-class logistic regression, logistic regression is for the binary cases, which exactly modeling this. If you still remember, what is the multi-class is that softmax function, right? The softmax provide you is P yi equals to 1 equals to E Z I over summation I from 1 to maybe capital L. There are total L labels, E to the Z to maybe J. Yeah, here's J. Yeah, so the predicted yi. Yeah. So, and this is actually, that's the probability. I should have X conditional. Yeah, so this is exactly what softmax function gives you, right? And this is the probability formulation, and that probability is just a parameterized form related to the X variables. And this is a multi-nodal distribution. And logistic regression uses a Bernoulli distribution to model. And it's just the parameter of that Bernoulli distribution is a function of X. All right, so we already had this learned very nicely. Then let's see the other regime. What is the generative-based classifier? So generative-based classifier, instead of directly modeling P, C conditional X, it's modeling P, X conditional C. So it had the model, it's the generative classifier. If you have C1, C2 until CL, L different classes, you're going to have L different models. It's how do the first class, CL, C1, generating my example X. How do the second class, C2, generating my X? How do the L class generating my X? So this is the model it's modeling. This is the probability it's modeling. But this is not P, C conditional X, right? To be able to use MAP rule, what I need to have is P, C sub I conditional X. And you might already still remember the whole assumption there is it's easier to directly estimating P X conditional C, and then we're using base rules from P X conditional C to derive PC conditional X. So if it's hard to directly estimate from data, because our P C conditional X is a conditional probability, right? And we use base rule to estimate this from P X conditional C. Okay, I hope you still remember this base rule. And this is the base rule. So we are just assuming this is easy to be directly estimated from data, and then we are using this to derive PC conditional X. Because you need this to use the MAP rule to decide which one is the max. So the rule is, again, C star equals to argmax C I P C I. Yeah. CI from the set C1, C2 onto CL. Okay. Question about this. This is the fundamental idea of generative-based classifier. All right. Yeah, so that's the base rule. And if you look at this, I want to estimate this, right? And then performing, and then that means I need to estimate this and also estimate this. And assuming those are easier to be calculated from data. The only thing, I mean, if I want to get a precise PC conditional X, I also need to have PX in the denominator, right? However, So, however, if you see, I'm trying to do argmax, right? So the whole MAP operation is argmax. So whoever is the max C, it's the argmax operation, right? And to performing argmax on this, equivalent to perform on this, the denominator is not related to C at all. And also, no matter what CI is there, this is a shared value in the denominator, which means it doesn't change the ordering of C1, C2, or at all. That's why we don't need it if we care it's only the max operation. And that's the reason why when you normally see in the generative base classifier, what you truly calculated is only the denominator part. And you do not need the denominator because this doesn't change the argmax operation at all. It's proportional. The number here is proportional to the argmax operation, it's proportional to this. So that's why we don't need to calculate the denominator px. And then the only thing you need to calculate in the generative base classifier is px given c and also pc. Okay, so try to remember this, and this is how you do the calculation, and then you need to estimate from data to get this X congruency and also PCI. All right, and then you just use the PX congruency times PC, multiplying them together. And then for a specific X that you care, maybe on the future data, if you have the ability to represent this, and then you just perform argmax operation, you're going to go get the best classification. Whoever give me the best probability is the classification label I'm going to predict. And each one of them is a separate model. This first generative model is conditioned on C1, it's generating X. The second generative model is conditioned on C2, the third until the last, CL. They all generating X samples, but from different generative model. This sounds pretty weird for now, but when we do a concrete calculation, it will be very, very apparent. All right, so I hope you still remember this and understand this. Just to summarize, discriminative classifier directly modeling PC conjugate X, generative classifier modeling the data from PX conjugate C times PC, and they both use argmax operation on the C. Okay, so now let's see, this is your training data. Assuming we are given a training data like this, which you already had in the printout paper. So, and then the whole thing is, what do I need? What do I mean training in this? Assuming all the variables here are marginally variable, just discrete variables. So this is my x1 variable. This is x1, x2, x3, x4, and c. So the base classifier, the whole important idea is you're assuming, I hope you can read, every feature variable and also the output variables are random variable. So here I assume C, let's see, C variable, I assume it to be a Bernoulli distribution. And there are how many possibilities? It's only yes and no, right? So I'm going to switch to the next page. Now look at your printout paper. Okay, so I have x1 variable, x2 variable, x3 variable, x4, and c. So this is what I have. And they are all random discrete variables. So how many possible values for the classification, the output variable? Only 2, right? Yes and no. And in fact, this is C1, this is C2. And then how many random variable, so for the first random variable x1, how many possible values? So sunny, overcast, and rain, right? There are only 3. SOR, let's write it as SOR, SOR. Okay, and then for the x2, we have HMC, right? Hot, mild, and cool. HMC. And for the x3 is HN, high, normal. There's only 2. For the x4, there's weak and strong. There are only 2. Yes. Okay, so these are their possible values. So just keep this in mind. Let's see. We already said, I want to estimate the Px condition on C, right? So what do I mean Px condition on C? So how many x I need to figure out for the future data? Whatever that's x, I can figure out Px condition on C. So in the end, to train the data, I need to figure out Px on C, right? x1, x2, x3, x4 on C, and also PC, right? So in the training phase, I need to estimate them from data. It's easy to estimate PC, right? Because there are only 2 cases. C equals to yes, and C equal to no. Okay, so what is PC equals to yes from this table? So there's a total of 14 cases, right? And it's a Bernoulli variable, right? Whenever it's Bernoulli variable, its probability of head is number of head over all the number of cases. So here, let's treat yes as the head. So how many yes I observed? 9. And in total, I have 14, which makes it pretty easy, is the number of times I see yes over all the possible observations, number of training size, which is 9 over 14. And the PC equal to no is extremely easy because 1 minus P, yes, right? It's 5 over 14. All right, so now I have the PC part. I need to estimate the second part is this. So how many combinations I need to know for all the possible future data I can give P this given this. Given the C, for all the possible situations, I need to have 2 cases. One C equals to yes or one C equal to no, right? Let's just give an example. In the end, I just need to count. I need to count this combination. This is a combinatorial set, right? How many this combination appears over all the training data. One conditioned on a specific C. And that's exactly let me give you an example. X1 equals to S, X2, let me look for a one actually exists. H, and X3 equals to H, X4 equals to weak, conditional on C equals to maybe no. So how do you calculate this from the training data? So what I had is SHHW, condition on no, right? You observed it how many times? It's really that observation, you observed it, this combination. You observe SHHW and no. How many times? Actually, in your table, one time. And then over what? How do you get this probability? We're assuming this is also a Martinelli, it's a discrete random variable. This combination is a discrete random combination. Condition on C equal to no, right? Which means my denominator is the number of times no. Right? Yeah, it's the number of times you observe the no, which is 1/5. I think it's 1/5, right? 1, 2. Yes, it's 1/5. Oh God. Okay, who has question about this process? And then, because I have to do this for all the possible combinations of each possible values for each random variable, how many do I need to estimate from data? How many cases of this do I need to estimate from data? It's combinatorial of all the possible combinations of the values from x1, x2, x3, x4, and then condition on the no or yes, right? So this is 1/5, but also I need to estimate the other. This is 1/5. And I also need to estimate x1 equals to s. I need to, it's a little bit harder to write on the bottom, so go to s. x2 equals to h. x3 equals to h. x4 equals to w. Condition on c equals to yes. So what is this from this table? The same combination, the same feature combination, but now it's yes. It should condition on yes. SHHW, right? Do we have SHHW on the yes? Actually no, we don't have SHH in the yes cases, which makes this calculation as 0/9. Okay, so this just gives you a flavor of what do I mean estimating this type of discrete random vector from the data when there's a class variable I want to predict. So how many cases I need to estimate this type of cases? It's actually very easy to do the calculation, right? So the first x has 3 kinds. The second x has 3 kinds. The third has 2, 2, and then 2. So the number of whole that cases is sorry, it's kind of flashy. This thing. It's total of 72. This is actually our parameter to estimate. So this is the model of a generative Bayes classifier. This P, whatever combinations, conditioned on the C, each C, and this is the parameter you need to estimate from the data. And this is the parameter of your model, this generative Bayes classifier model. Question about this. This is very fundamental and this is the key. Sure.
So are you gonna multiply those results by PC later?
Yes, so this is the training phase, right? In the training phase, you really just estimate. In fact, this uses the assumption called this is a discrete Martinelli distribution. Its MLE parameter is the counts over it's this count. So the number of cases you preserve over all the number of cases. And that's the classic MLE solution for Martinelli distribution. All right, so this is just a more, it's in the end, I try to more concretely do x2, x3, 2 cases, x4, 2 cases, x1, 3 cases, and C. All right, this is the 1/9 and then 0/9. I try to show you almost the same. You just directly estimate from data. And there's a total of 3 times 3 times 2 times 2 then times 2 number of parameters to estimate plus 2 more, which is the PC equals to yes and PC equals to no. It all sounds pretty complicated, but in fact, this is your model. The model essentially is a lookup table. And the lookup table is, so the first case is PC, PC1 and PC2. This is exactly the PC1 and PC2. And we have only 2 C here. And then the X given on C is, so this is condition on the C1, this is condition on the C2, and this is all the combinations. You need to have all the possible combinations. So when you have sunny, hot, I mean, let's just show one. It's really just enumeration. There's no trick at all. Just enumerating all the possible combinations among the values. So for this case, you just have weak, strong, and then with the high, and then you move the high to normal, and this has weak, strong. It's just enumeration of all the cases. And this is a lookup table of conditional probability. And that's how you get, or either you're just counting how many cases this combination exists. One for the yes cases, you put counts here, and over all the possible yes cases. And how many of this combination exists in that training table for the no cases, and if you put a count here, and you put the number of no cases as the denominator, this is how you get the probability, that conditional probability. And then how do you use it? When you use it is when there's a future data, assuming, let's just give you a case, maybe, I think I give you a case is SCH, the S, And you really just do lookup. What is in that lookup table you learned from the training data? This is the future data. What is the corresponding SCHS condition on the yes? What is this probability from that table? And times P yes. And then what is this combination condition on the no? That probability from the previous table, the no table. And then times P C to the no. And then for these two calculated values, which one is bigger? And then you assign the classification as the one give you a bigger probability. Sure.
So why do we require to like save that table? We can compute it on the fly.
On the fly,
Yeah, I mean, if we have like training data saved somewhere, so we can always.
if you have training data of what?
Like the from the training data, we are learning this table and that.
Good question. I'm going to talk about that later. Okay, so how many features do I have here? Four features, right? And how many combinations do I have? Oh, I already calculated. It's the 3 times 3 times, yeah. So, yeah. So, let's use extreme case. If this is for English dictionary, which is actually your homework 5. The x1 to xp is all the words. So what is p here, roughly? The p, so the p is roughly the number of is this p. P is about 30,000. Okay, so assuming there's only two possible values for each x1 until xp, exist or not exist, right? You can describe your articles always using, is that word exist or not? How many probability you need to get in that case? First, there are two combinations, exist or not. Second word, exist or not. Third word, exist or not. Until the pth word, exist or not. So, how many parameters, assuming I'm predicting sentiment thumb up or thumb down? It's a positive or negative. So this is my x1 to xp. And my y, my c is good or bad, I mean, sentiment, good or sentiment. Yeah, I can write a thumb up, although I need to draw less, up or down. Yeah, let's do that. Up or down. So, how many parameters do you need to estimate for this case? Use the same calculation, like this lookup table. 2, 2, 2, 2, which means 2 to the p, and then times 2, right? Assuming there's total L parameter, L class labels, this is the size of that lookup table you have to estimate. Okay, so I think you know what's 2 to the p, right? 1p equals to 20. What is 2 to the p? 2 to the 20 may be feasible. 2 to the 30k, is it even possible or not? But think about it. 2 to the 30k. There's no way. But I'm just trying to show you, but this is one current solution. And there's no way to calculate on the fly. That just to tell you first, right? It's a huge number of things to memorize. And also because of this, we're going to do some kind of simplification later. But still, with 2 to the p, if p equals to smaller than 20, I think it's still feasible. Yeah, smaller than 20, 2 to the 20 is, I cannot do calculation now, but I think it's feasible, 2 to the 20. Okay, so just give you a rough idea, and you need to estimate this from data. and the size grows really fast when you have more features. All right, and then the testing phase, you really just look up. You look up for that specific combination in your test data. You look up what is that one from the yes class. It's really generative model, right? Sorry, it's really this model. Yeah, here. So what is the PX from yes? What is the PX from no? Or until the CL class. That's exactly what you're calculating from the generative model. Or in this case, the generative model is the lookup table. All right, question about this. And this is the simplest ever discrete generative model. But clearly, this is not feasible.
How this will work if we have continuous variable?
Good question. It's after this. Yeah. So this is just discrete random variable, right? Okay, I think here it's almost I'm repeating what everything I covered before. Now, like I said, you have to have a lookup table of 2 to the p times the L number of classes to perform the previous lookup type of discriminant random variable generation. That's not feasible at all. The whole reason is, there are just too many things here. Like 2 times 2 into maybe 2 equals to 2 to the p, then times the number of possible classes. You need to memorize this through estimating or counting from your data. And then later, when you have a future data, you need to search, or actually not search, retrieve a specific case from this 2 to the p times L lookup table. This is not feasible. So that's why people have some kind of simplified assumptions, which the mostly used is called naive assumption. The whole naive assumption is extremely actually simple. I'm assuming all the input variables are conditionally independent given the output variable. So, equation-wise, it's really easy. It's just the join probability. So actually now we only do this part. So this is a join probability, right? It's a join probability of x1, x2 onto xp when conditioned on the Cj. So it's a join probability. And I just assume all this variable are conditionally independent from each other. If you still remember the conditional independence assumption, which makes it equivalent to when you're conditionally independent, this join probability equals to a multiplication of each variable conditioned on that specific class variable. And I don't need to do the joint anymore. I only need to just estimate x1 condition on Cj, x2 condition on Cj until xp condition on Cj. So, and this is exactly that part. This is a simplification. So it's not because this exists, right? This is my assumption. I'm assuming the join probability equals to the multiplication of each. All right, so now this part is super easy to do the calculation. Now go back to the graph. So what do I mean the models now if I have this assumption? So what is my model now? What do I learn from my training data? So let's see, whenever, we had that before, to perform PCJ condition on x1 onto xp, and that's my classification rule, right? And I need to use this is px1, x2, xp condition on Cj times pCj. And now it's equivalent to px1 condition on C, px2 condition on C, until pxp condition on C, Cj, specific Cj, and then times pCj. So this is the model I need to estimate from data, which means to perform future inference, I need to know this, 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 and this. And this is the model parameter I need to estimate for my naive Bayes classifier. And when you have a future sample has specific values, and then you just look up. So again, this is still a lookup operation, but the lookup operation is, I think I have a page. Yeah. So maybe let me write it here. So what I need to estimate from data now is from training data is PC. It's actually in fact this. It's just exactly this. And each one of this is a table, right? So go back to see your current, that table. How many parameters do I need to estimate from the training data for this? How many for this? How many for this? How many for this? And this is the same thing, right? Still P yes and P no. Let me actually add a page because I think it's important. Yeah. Yeah, so, okay. Stopping and responding, but I think that's okay. So, yeah, I think I can stay right there. Yeah. So, in the end, to be able to, as when there's a new data coming in, I need to look up this. I need to look up this, and then I need to look at this until look up this, right? This means the thing I need to estimate from my data becomes for x1 and condition on C, yes, and condition on C, no. How do I write easily? So x1 has how many cases? S, O, R, yeah, okay, so it's the C. So I need to estimate this, right, from data. P x1 condition on C, and the x1 equals to S, x1 equals to, sunny, and then x1 equals to overcast, and then x1 equals to gray. And one condition on C is yes, C yes, C yes. And this is the one I need to estimate from data. So let's just use an example. What is sunny given yes? When you look at your table, what is sunny given yes? So there are a total of 9 cases in the yes, right? Which is equivalent to number of sunny and yes over number of yes cases, which is equivalent to, it's a little bit hard to count, 2 over 9. Yes, 2 over 9. Yeah. And then you just do the same for O and yes, and R and yes, And then you do the same thing, S, O, and R for C equals to no. And this time, it's just the number of counts, sunny and no, over the count of no. What is it? Sunny and no. Sunny and no is, how many sunny? 3? Is it 3? 3 over 5. Okay, and this is, you just perform the same operation on x1, x2, x3, x4. And then you also need to have P C equals to yes. Without anything, it's just that's called prior probability. P C equal to no, what is it? I think we already had it, is 9 over 14 and 5 over 14. And this is your naive Bayes classifier model. And this is exactly what you're going to implement in the homework. And the only difference is our x1 until xp are English words. And you need to count. You need to count how many times, how many samples that word appear, and also the class label is maybe positive thumb up over the number of positive articles. All right, okay, so this sounds so easy, right? But it's the procedure is important. All right, and then when you perform, this is the same thing. And in fact, what I did there is by assuming this is a Martinoli distribution. The whole thing I'm using counting is the Emery solution by assuming this is a Martinoli distribution. When the binary case is Bernoulli distribution. But actually, there are many other possibilities, which one of the possibility is called multinomial distribution, which is used the most in the bag of words representation based naive Bayes classifier, which we're going to cover next lesson. So there's whenever people use bag of words representation, they normally assume, so this is my word, maybe good, condition on thumb up. So they're not just care about exist or not exist. What they care is number of times it exists. And how do you represent when this is an integer or it's a frequency? We can't just do this count-based MLE. It's not completely correct. So in those situations, it's not being assumed as a Martinoli distribution anymore. They need to use a multinomial model to represent. So there are some differences and which we're going to cover in detail next lesson, especially bag of words representation is using, we need to use multinomial distribution to model bag of words representation. All right, so in the learning phase, you really just count. So you count the prior, then you count each value, possible values by condition on all the different all the different class output cases. Then let's calculate how many parameters you need to estimate in this. So let me come back to the example. Okay, so for x1, how many examples do I have? How many parameters do I need to estimate? One, two, three. 3 times 2, right? 3 possible values, and then L possible class. So for the first, it's 3 times L equal to 2. For the second feature, same thing. 3 times L, 2 times L, 2 times L. Okay, so in total, how many parameters do I have in a naive case? 3 plus 3 plus 2 plus 2 times L. So it just in our case, L is 2. L equals to 2. How many parameters? 20? Yeah, it's 20, right? Okay. And plus the 2 prior, plus 2. In total is 22 parameters. So versus the previous case without the naive assumption is 72 plus 2, right? So that's the no naive case. Is 72 plus the 2 prior, which is 74 parameters. And in this case, we have plus 2, the 2 prior is 22 parameters. So we have much fewer number of parameters. Okay, now let's make it even more extreme. If I'm doing x1 until xp, each one of them I have only 2 cases, 2 possibilities, x1, x2, until xp. How many parameters in this case I need to estimate? Each one of them have only 2 possibilities. 2 plus 2 plus 2 until the pth case. So in total, this gives me 2p, right? And then times the L. That's because for each class you need to generate, you need to have that condition on each possible class. So this is, let's do the plus until this give me 2pl. And this is versus 2 to the p times l in this non-naive case, right? And you can tell, and there's a reason why we need to have the naive assumption. So even if p equals to 30k, how many parameters do you need to estimate if this is 30k? Assuming L is 2, 120k parameter to estimate. And this is still feasible when you have large enough text samples. P 30k is feasible if you do the naive assumption. All right, so this is the key, the whole thing about the naive-based classifier. Lookup table. Yeah, so I already talked about it, and then when you have, you can do Bernoulli, binomial, and then, so this is a more generic case, right? Assuming the first feature has K1 possibility, K2 possibility up to KP. It's really a summation of K1 to KP times the L. And then during the testing phase, what do you do? And there's an input number of X, and then you just calculate P A1 condition CI, A2 condition CI, until AP condition CI. You multiply those things you got from the lookup table and times the PCI, and then this will have C1 until CL numbers. Whoever give me largest of this number is the predicted class label, C star. So in fact, this type of naive-based assumption can be used through a graph type of representation. It's if my variable, if the parameter I need to estimate it is conditional on some variables, and I write those variables as my parent. And the naive-based classifier can be represented by the simple diagram, graph diagram is, I need to estimate, because the C has no parent, right? I don't need to estimate anything. I only need to estimate PC. That's exactly it was trying to show, PC, because each of these X features, they are conditioned by the parent of C, and then I need to estimate for each one of them the variable I need to estimate is the possible values. Let's use x6 as example. X6 into some kind of maybe x61 possible values conditioned on the CI. And for this type of edges, we just need to estimate all the combinations of the values from x6 versus the values conditioned on the values of all the possible C, which is exactly those naive conditional probability we are learning. So this whole diagram shows everything about the naive Bayes classifier. We need to estimate PC, only PC, and then we also need to estimate Px sub j of a specific values conditioned on each possible Ci. Yeah, maybe K. Maybe P, yeah, it's some kind of possible values, yeah. Let's just see hot or cold or whatever, yeah. Okay, so whatever I did before, it's essentially assuming this as a Martin-Rowley distribution. That's why the parameter estimation or MLE solution can be estimated through counts. So the number of xi is the specific values at the same time. C is a specific Cj over the number of times the specific Cj exists in your training data. Yeah, so this everything we covered. This PC equal to C, Px condition on C, and then you just and this tells you this diagram guarantees x6 and x5 or all the x are conditionally independent from each other when given the C variables. It just because we have a shared parent C here. So this is just called a graphical model of Bayes net representation. So if you don't completely get it, don't worry. I just want to give you some kind of more advanced version to talk about Bayes model. So because I'm showing you a graph, right? And then there's something means, and this is a simplest tree graph. But in fact, you can have a lot more complicated, right? So this is so easy. All in C controls x1, x2 until x6, but maybe your data is not this way. So maybe your data is assuming I'm trying to predict a child diabetic or not. And there will be some parameters, some features are dominating parameter like age parameter. The age feature versus maybe weight. Let's think about age, weight, and disease stage. C is the diabetic or not. And there's maybe, I'm too slow today, but the age and weight. So if we have only the naive Bayes model, the correct diagram is age and weight, only condition C, right? But in fact, that's counterintuitive because the weight of a children clearly will be also dependent on the age too, right? So this, and just the one we show you is the simplest ever, only naive assumption. But in the real world data, the relationship among the feature variables and also relating to the output variable is much more complicated. And this type of relationship is called Bayes net. When you learn it, you actually can learn the relationship among features from data, not just using the simplest naive assumption. All right, so this is what I showed you, the lookup table view in the naive Bayes classifier, and I already did. These are the parameter two. They're also lookup tables. And then you can do the calculation like we did. Then the whole thing is counting. And then there are a total of 20 parameters we already did. Yes. Then in the testing phase, let's give you an example is SCHS, and you want to predict based on the naive Bayes classifier. Then how do you do? In fact, you just look up. You look up what is the PC1, yes, and what is PC2 or no. You just get those numbers from that table, prior probability table. You also look up what is P sunny given C1, what is P sunny given C2, what is P cool given C1, P high given C1, P strong given C1. You got to look up from those tables, you do the calculation, the same thing for the C2 class, the no class, and then you just get the numbers. The first give you 0.0053, the second give you 0.02, and this is bigger. So that's why we predict this as no. Is it clear? This is completely how you're going to implement in your homework, to implement a Bayes or naive Bayes classifier. I think we're pretty good because I already covered without assumption you have 2 to the p. With the assumption you have 2p times c. Yeah, 2 to the p times L, 2p times L. And this is linear to the number of parameters. This is exponential to the number of parameters, which, of course, exponential is not scalable to the large p. And I think the last is 1 minute, is one thing. There are situations like this. Assuming there's X6 is muscle ache, and the C is with flu or without flu. There are situations because you have to estimate muscle ache, if muscle ache equals true condition on flu or not flu. But maybe in your data, there's no muscle ache, but no flu. And that makes the count of this as 0. This is a probability 0 case, right? They give you probability 0. Why this is actually extremely bad. The reason is when you're performing the prediction classification, you have to do PC equals to flu, X1 condition on flu until X6 condition on flu. And then also PC equals to not flu until the PX6 condition on no not flu. If any of the numbers there is 0, it doesn't matter what the other numbers are. It will be just dominated by 0. So this type of naive Bayes classifier for the discrete case, you have to try to avoid 0 probability. And because it doesn't work when you do this multiplication, joint probability estimation. And you have to try to avoid the 0 probability. But there's a lot of cases we actually did. Wait, I have this SO whatever cases coupled with output yes. It just not exist in my training data. It doesn't exist, then how do you do with it? There's a lot of trick called smoothing trick. Simplest trick is you just plus 1 on the denominator plus maybe the number of possible values in the denominator, and this can give you a good, at least good baseline for the non-zero case. There's a lot of different, the Laplacian smoothing, there are actually many types of smoothing, and this is one of the very big topic in information retrieval and natural language processing. And to summarize, we are trying to predict using probabilistic models and using through the MAP rules, because the P, it's for the discrete case, the number of parameters to be estimated from the data is exponential to the P. So that's why we have a naive assumption to make the number of parameters linear to the P. And next time we're going to talk about Gaussian Bayes classifier, because here I'm assuming all the variables as discrete, either Bernoulli or Martinelli variable. But how do you handle when it's continuous, right? The most classic continuous probability for most